Good day everyone, my name is Moe Shahram and this course is Physical Science Survey PSCI 10 at West Valley College. Today we are going to talk about Chapter 7 about model and theory of atom, and we'll discuss a little bit about how the theory of atom evolved throughout the history. We begin with the evolution of theory of atom, and then we look at issues that scientists had with the classical model, and we will talk about how the concept of quantization of energy came about and how it helped to develop the quantum theory of atom, and also experiments such as photoelectric effect that prove that light can also behave like a particle, a bundle of energy. We then recognize the dual nature of the light, behaving like wave as well as particles, and then we look at the new theory of atom, how it evolved and eventually got into a point that atom was described by new concept of quantum physics. We move on to talk about how the elements and electron configuration in elements relates to such theory. And then we discuss a little bit about how the periodic table relates to the concept of quantum physics. And we conclude with the notion that when we go into atomic realm and scales, measurements are not exact anymore. So we will not be able to exactly measure a position or velocity of a given particle. And we will see how we're going to deal with that by the uncertainty principle. So looking back in the history, way back in 2,500 years ago or so, scientists thought that all matters on the earth, on the universe, basically made out of 4 elements: earth, water, fire, and air. A little bit later, other scientists such as Democritus came along and said that elements can be divided in half and continue dividing in half until you get to a point that you cannot divide it anymore. And that was a notion of the atom. Tiny little indivisible particles made everything else up. It was until about early 1800s that John Dalton, a botanist, was studying some pollens under the microscope. They had, a relatively modest microscope that they could see things on the order of hundreds of micrometer under the microscope. And basically noticed that all these pollens that are visible, they are randomly moving around with no apparent force that is causing that random motion. Eventually he concluded that there must be other tiny particles that are not visible under this microscope that are pushing these bigger particles around. And that was the beginning of experimental evidence of atoms. They're not visible, but they're there, and their effect is evident. Let me show you this video animation about this experiment.
So we're going to have a look at the idea of Brownian motion. This is useful because it helped indirectly to confirm that atoms exist. You're in a darkened room, the air is still, and the bright lights are streaming through the window. What do you notice about the dust particles? The black circles as they pass through the beam of light. Pause the video and think about this. Press play once you've made up your mind. The answer is that the dust particles are moving randomly. Did you see it? The dust particles are not always moving downwards, but are moving in all directions. The dust particles are very small and are supported by a fluid. In this case, that fluid is a gas. You are unable to see the gas particles directly because they are too small, but you can see the larger dust particles. The reason that the dust particles move randomly are because of the gas. We know that the gas is there because every time we move our hand through the air, we feel them against our hand. Try it now. Continue when ready. The particles in the air move in random directions quickly. This means they'll have many collisions or will bump into the dust particles many times. Each collision between air particles, very small coloured circles, show how the dust particle, the black circle, moves off in a new random direction. It's a bit like a game of snooker, where there are millions of marbles which collide with larger, observable particles like a ping-pong ball. This effect was first observed by scientist Robert Brown. He was looking at pollen grains suspended in water under the microscope, and he wondered why they jiggled around. He thought that the pollen was alive. It was later that scientists realised the importance of his discovery. Now, here's a challenge for you. Thinking about what we know about dust particles, can you explain why the pollen grains appear to be jiggling randomly? Pause the video and continue when ready. In summary, the fluid is no longer a gas, but is a liquid, water. The pollen grain is colliding with many water molecules. Each water molecule is too small to see, but we can see the combined effect of their collisions on the pollen grain as it moves randomly. This effect is known as, you guessed it, Brownian motion.
All right. Then around 1807, John Dalton was a scientist who actually proposed that atoms are made out of a very dense solid sphere which is indivisible, and they react with other atoms in a manner of discrete and in certain proportions. That was called billiard ball model. Let me show you a little bit of this video, but you can watch the rest yourself. So let's start from the beginning.
To understand the first scientific atomic theory. The first scientific theory about atom was put forward by an English chemist, John Dalton, in 1803. He described an atom as a solid hard sphere which is neutral with no charge on it. Let's understand the postulates given by him in his atomic theory. Composition of matter. Consider an element, for example gold. See what it's made of? As you can see, it is made of particles of the same type. Whereas a compound like water is made of particles of two different types. A closer look at the mixture of iron and sulfur enables us to see that it is made of very tiny particles of iron and sulfur. Dalton called these tiny particles that matter is made of as atoms. All forms of matter, whether an element, a compound or a mixture, is made up of very tiny particles called atoms. Indivisibility of atoms. Consider a piece of the metal gold. When you try breaking a piece of the metal, gold, into smaller pieces, at some point it becomes impossible to break it any further. Dalton called this smallest particle of matter an atom, and he further stated that the atom is indivisible.
You can watch the rest of this on your own, but for now this part is enough. Dalton concluded that all matters are made out of indivisible atoms. An element is made out of identical atoms, and different elements have atoms with different masses, and chemical compounds are made out of atoms in a specific integer ratio. Now we'll talk about this when we talk about chemistry. Atoms are neither created nor destroyed in any reaction. So all of these conclusions were fine, and it is okay today, except one, and that is the first one. Today we know we can break the atom, we can see the subatomic particles in accelerators, but the rest of the conclusions were fine. As the time goes on, in late 1897, another scientist, J.J. Thomson, was experimenting with the cathode ray tube, Now, cathode ray tube is a tube that is vacuum. There's no gas or particle inside that tube. And you have two electrodes that you can connect it to a high voltage by means of heating an element. A beam started to showing. And that beam noticed at the screen, which was coated by fluorescent material. And this is one kind of example of the cathode ray tube, which we do have in the lab and we can demonstrate in live situation. As you can see, when you hold a magnet, the beam that is emerging diverted. This basically led him to declare that he has discovered a negatively charged particle. They didn't know quite well what was that negatively charged particle. By just applying a magnetic field and electric field to this negatively charged particle, which causes it to divert in certain angle, they were able to find the ratio of the charge of this particle, whatever it was, to its mass. So this was a discovery that J.J. Thomson made. So let me show you the animation of this one.
A cathode ray tube is the forerunner of the television tube. It is a glass tube from which most of the air has been evacuated. When the two metal plates are connected to a high voltage source, the negatively charged plate, called the cathode, emits an invisible ray. The cathode ray is drawn to the positively charged plate, called the anode, where it passes through a hole and continues traveling to the other end of the tube. When the ray strikes this specially coated surface, the cathode ray produces a strong fluorescence or bright light. When an electric field is applied across the cathode ray tube, the cathode ray is attracted by the plate bearing positive charges. Therefore, a cathode ray must consist of negatively charged particles. We know these negatively charged particles as electrons. A moving charged body behaves like a tiny magnet, and it can interact with an external magnetic field. The electrons are deflected by the magnetic field. As expected, when the direction of the external magnetic field is reversed, the beam of electrons is deflected in the opposite direction. In 1897, J.J. Thomson, an English physicist, determined the charge-to-mass ratio of an electron. He adjusted the electric field so that the electrostatic deflection, theta E, was the same as the magnetic deflection, theta B, and was able to calculate the charge-to-mass ratio of an electron using the following equation, where E is the applied electric field, theta is the angle of deflection, B is the applied magnetic field, and L is the distance traveled by the cathode rays. Thomson determined the charge-to-mass ratio of an electron to be negative 1.76 times 10 to the 8th coulombs per gram.
Okay, so you don't have to worry about the equation and how we got this ratio of charge over mass. That's beyond the scope of this course, but just know that by this experiment you can obtain that information. At that time they didn't know, they didn't call these electrons. So this negatively charged particle, which later on was called electron, identified as a fundamental particle. There were new discovery. People thought, wait a minute, now atoms are neutral. Now we have somehow a negatively charged particle emerging from this element. So there must be a positive charge involved in the atom. So J.J. Thomson proposed a model, and that model is known as plum pudding. It's a mixture of a positive and negative charges inside the atom, uniformly distributed. And as a result, you must have both charges. So this is about around 1903. They knew the ratio of this negatively charged particle to mass, but they didn't know what the charge of this particle is and what is the mass of this. Another scientist, Robert Melton, around 1906, he set up an experiment to find out what is the charge of these particles and what is the mass of these particles. He basically had a chamber that he could put some tiny little oil drop, spray the oil drops inside his chamber. Now the oil drops are visible, and there was a hole here, and then the oil drops can drop through the hole, And there were two plates. Top plate was connected to a positive side of the battery and the bottom one to the negative side. If these oil particles are charged somehow, if it is negatively charged, they'll be attracted towards the top plate. If it is positively charged, they attract towards the bottom plate. Then he actually shined a source of radiation that could emit X-rays. Now, X-rays emitted at these tiny little oil drops would add charges to it. Oil drop, obviously they have a little bit of a mass that the gravity is pulling it down. Now, if it is charged negatively, they also be attracted towards the top plate. As a result, these two forces are now in place. One force is due to the gravity, and the other force is due to Coulomb force. If you can have these two forces balance each other, then you have that oil drop suspended in air. And when that happens, the two forces are equal, so you know what the forces are relate to which parameters. On one side, gravity relates to the mass of the oil drop. On the other side, Coulomb force depends on the charge of it. So you equate these two forces, and from there you can measure the mass and charge of these particles. Now, let me show you this animation for this experiment.
In 1909, Robert Millikan, working at the University of Chicago, succeeded in measuring the charge on the electron. He allowed a fine spray of oil to settle through a hole into a chamber where he could observe their fall. The top and bottom of the chamber consisted of electrically charged plates. He introduced a source of X-rays which can cause creation of charges when they strike matter. Charges produced by the X-rays attach to an oil droplet, producing one or more charges on the droplet. When there is no voltage applied, the fall of the droplets is determined by their mass and the viscosity of air through which they fall. When a voltage is applied, the droplets that have a negative charge will fall more slowly, stop falling, or even rise, depending on the number of charges on them. By adjusting the applied voltage and observing the droplets both with voltage off and voltage on, Millikan was able to determine that the charges on the droplets were all multiples of a smallest value, 1.6 times 10 to the minus 19th coulombs. He took this to be the charge on a single electron.
Great. So now we have the charge and mass of these negatively charged particles. Now it's called electron. But still, the model was J.J. Thomson's model, plum pudding. So all the positive, negative charges are mixed throughout the volume of the atom. Another scientist, Rutherford, in 1907, was doing an experiment. And his experiment was like he had some radioactive material. Now, the radioactive material, as we will see, emits three types of rays. One is called alpha particle or alpha ray. Another one is beta. Another one is gamma. Alpha is basically consists of nucleus of the helium. That is 2 protons and 2 neutrons constantly emitted from this radioactive material. He had a thin gold foil here, and he directed this alpha particle to this thin film. He had a detector, a fluorescent screen formed in a kind of a circular fashion. He noticed that a lot of the alpha particles emerge from the other side of the foil and hits the screen right back there. So that was kind of expected. But every now and then he noticed that some of it divert to some angle and some even recoiled back all the way back in the opposite direction. And that was puzzling at the time. Eventually he concluded that if the atom is the model that J.J. Thomson proposed, all these rays of alpha particle must go through, and every now and then they could probably divert a little bit. But if the atom is constructed in such a way that all the positive charges are concentrated in the center and the negative charges around it, then these alpha particles being reflected back all the way could be as a result of this model. So he came out with a new model that the positive charges in atom are all concentrated in the center of the atom, and the negatively charged ones are all surrounding that positive charge. So let me show you an animation of this one.
In 1910, Rutherford and his co-workers were studying the angles at which alpha particles were scattered as they passed through a thin gold foil. Most of the alpha particles passed through undeflected. However, a few were found to be scattered at large angles, some even back in the direction from which they had come. This meant that they had collided with an object much more massive than the alpha particles themselves, yet so small that only a few alpha particles encountered them. This atomic level view shows what is happening. Most of the atom is occupied by the low mass electrons. The nucleus is small and massive. When an alpha particle encounters a nucleus, it is scattered at a large angle.
That was his contribution. And his model was proposed that the nucleus contains all the positive charges, and the electrons are kind of orbiting or circulating around that positive. Let's look at what happened in span of 100 years. So starting from 1807, from Dalton model to J.J. Thomson to Rutherford model. Around 100 years, the atomic model evolved to this state. Let's see some properties of atom. Atoms are obviously very small, the order of 10 to the minus 10 meter. 10 to the minus 10 meter is called angstrom. The nucleus is very, very tiny portion of this, and atoms are mostly empty space. For example, the size of the hydrogen atom with one proton and one electron is roughly about a quarter of angstrom. Today we know that atoms are very tiny, they're numerous, and then they're constantly moving. After the Big Bang, the atoms were later on formed, and they're with us today, and they will be constantly recycled, scattered to the space, reform again to generate another solar system or a star or a planet or what have you. Richard Feynman, he described them very well. He says these are tiny little particles that constantly moving, they're in motion, kind of attract each other up to a certain distance. But when they get close to each other, if you try to push them further together, they resist. That was his description. Today, we are able to actually take images of atom. How? We will talk about that later on, but we use what we call electron microscope. In this picture here, taken by a transmission electron microscope, you can actually spot hydrogen atoms. These are set on some kind of a graphene substrate. And you can also see the carbon atom, which are kind of bigger. So the question now is, which of the following are incorrect statement about the atom? So what we learned so far, atoms are smaller than the wavelength of visible light. Well, if you remember, we talked about wavelength of visible light being around 400 nanometer to 700 nanometer, and we just talked about the atomic size is 10 to the minus 10 meter. Obviously, nanometer is 10 to the minus 9 meter. So this statement should be true, right? Atoms are mostly empty space, just as the solar system is mostly empty space. So we know that and talked about it. Atoms are perpetually moving, which we know, true. Atoms are manufactured in plant and in human. This is incorrect. They just move around and recycle and connect with other atoms to form different compounds and so on. So this is the incorrect statement. In summary, you can watch this YouTube video, which is very interesting, and you can do this at home on your own. That puts together all these things that we talked about with some more animation and details if you're interested. it's a good video to watch. So you can just click on this link and it should come up. How do we identify these elements, these atoms? Well, we identify this with a symbol as the name for the chemical element. And then we also show two numbers, one on top and one on bottom. The Z number represents the atomic number of proton in that atom. A number provides the number of proton plus the neutron. So we have what we call the atomic number, which is the Z number, mass number, which is the A number, and then we have atomic weight, which we'll talk about in a minute, and we have isotope and ion. Let's talk about these. Atomic number, as we said, represents number of proton, and if the atom is neutral, that's equal to number of electron. Mass number is basically number of proton plus number of neutron. Here in this case, carbon has 6 proton and 6 neutron, carbon 12. Mass number is 2. Now, atomic weight, because some of these elements have a kind of a different version of them in nature, and we call that an isotope. And everything is the same in those versions except the number of neutron. You have carbon 14, which has 2 additional neutron, but the number of proton is the same. Isotopes have the same number of proton, but different mass number. So how do we find the atomic mass of these? Well, we look at the average of these isotopes that happen in nature, and they're abundant. And we use that to kind of average things out and find the atomic weight for each one of these elements. We use the atomic mass unit in describing that. Now, atomic mass unit is easier to deal with rather than writing 1.67377 10 to the minus 27 kilogram all the time. So we say that is 1 atomic mass unit. And we use a reference, and that reference is carbon 12. 1/12 of mass of this carbon 12, it's equivalent to 1 unit, 1 atomic mass unit. So this is a good reference unit that we use in order to identify the atomic mass of all the other elements. Let's look at the nitrogen. Nitrogen has 2 isotopes, nitrogen 14, pretty stable, and 7 protons. Mass number is 14.00307. Why is that? Because the abundance of this is actually 99.6% of the nitrogen made out of this nitrogen 14. For the nitrogen 15, that's also stable, but it has 8 neutrons. Therefore, the mass number is 15.001. How do we get that? I'll show you in a minute. But we need to know what percentage of nitrogen 15 exists in nature on the Earth. That's about 0.37%, so it's not much. So how do we find the atomic weight of the nitrogen, which is this number here? Well, we take the isotopes that are available there. Nitrogen 14 is 99.63%. Nitrogen 15 is 0.37%. Use that percentage times its atomic mass unit and average it out. The atomic mass unit times 0.37%. Atomic mass unit of this one times 0.9963. And then add them up, take an average, you get 14.0067. So that's what you see on the periodic table. Here is another example of isotope of carbon. As we said, we have carbon 12, 6 proton, 6 neutron. The weight is given, the atomic mass unit is 12 because that's our good reference. We take that as a reference, and the abundance is 98. 13, it's 6 proton, 7 neutron, and but the abundance is very low, 1.1009. Carbon 14 has 8 neutron and 6 proton, and the abundance is 1 part per trillion, And we're going to talk about half-life because this is a radioactive material. Here is an isotope of hydrogen. Hydrogen is one proton, one neutron, but if you have two neutrons, you have deuterium. And then if you have three neutrons, you have tritium. So with these, you can make heavy waters that are used in nuclear reactors. So looking at a periodic table, all the elements are identified here. And we're going to talk about this later on and also in the chemistry part of this course. But just, an example of a periodic table. We are now in the beginning of 19th century, and we still have issues with describing the model of atom, because we try to explain the atom based on classical theories and classical parameters that we know, and we're running into trouble. One issue was that if electrons are orbiting around the nucleus, and we know electrons now charge, and we learned from electromagnetism that a charged particle that is accelerating must radiate some sort of electromagnetic radiation. If that is happening, it must lose its energy constantly. If it is losing energy, it has to collide and collapse with the nucleus, because there's a negative charge and the nucleus is a positive charge. Bang, orbit of electron, and this thing accelerating is radiating. Then this thing is going to go like this and eventually and collapse. But this doesn't happen. We know atoms are stable. So that was one issue that scientists were puzzled and trying to figure out what's going on. Another issue was that they knew at the time that any object emits radiation. The intensity actually of radiation depends on the temperature and frequency of that radiation. This behavior of intensity of the electromagnetic radiation, in this case visible light in this region, shows that as you decrease the wavelength, as you increase the temperature, the peak of the radiation actually increases. The light intensity or electromagnetic intensity increases. And that relation was given by this formula, which tells you some number divided by the temperature of that radiation. Knowing that, then they knew that the frequency and intensity are related. In fact, they knew that intensity is proportional to the square of frequency. Okay? That means as the frequency increases, that means the frequency increasing to the left. The intensity has to increase as a function of frequency squared. As the frequency increases, this peak must go higher and higher. And when you get to, say, this region, which is ultraviolet frequency, this should go to infinity. But that doesn't happen. Actual curve looks like this. Okay? They couldn't explain that. All right. This was called ultraviolet catastrophe. And they didn't have any explanation for that. But then came along Max Planck, and in 1900 he was able to address this issue. He said that the energy that is actually emitted comes in a quantized manner, a discrete and a specific amount of energy basically emitted. The energy of that discrete amount is proportional to the frequency of light or electromagnetic radiation. And he came out with this very simple and important equation that the energy is equal to a constant H, which we call it the Planck's constant, which is 6.63 10 to the minus 34 joules second. Now look, this constant has a factor of energy in its unit times second. This was the first step towards quantization of energy in atomic scale. What does that mean? Well, it means energy can be only in a discrete value. It's not like continuous value. The analogy is it's like a bucket of water rather than a continuous water coming from the hose. That was the first step. Let's do an example on this one. So what is the energy of red light? Now objects are emitting electromagnetic radiation with different frequencies. Say having a red apple and you shine a light on it, white light, and then you see the red. So it's emitting a red frequency. We know the frequency of the red color is 5 × 10⁻14 hertz. So all we have to do, multiply that with the Planck's constant we just introduced, and then you get that much energy. 33.15 10⁻20 joules. Now, if you look at the blue light, what is the energy of blue light emitted? We know the frequency of blue light is 7.5 10⁻14 hertz. You multiply that by Planck's constant, and you get almost 50 10⁻20 joules. And look at it. Energy of blue light is larger than energy of red light. The energy of these emission depends on the frequency. Then came along Einstein. He actually look at the other side of the coin. He says, oh, wait a minute. We have light, which is emitted like a wave, and it has a frequency. And we know what the energy of light is. Okay, so E is equal to H times F. And this behaves like a wave. But he, through the photoelectric experiment, was able to show that this light can also behave like a particles. This experiment was done prior to him, but he redid that in a manner that he had a metal electrode here and another electrode here. So he connected these two to a positive and negative of a battery. And then he put a little amp meter to kind of measure the current that goes through this circuit. Well, normally nothing goes through circuit because this whole thing is in a kind of a tube or a bubble that there's no gas in it. It took all the gas out. Then he started shining light on it. Initially, he didn't see anything. But as he changed the frequency of the light, he noticed that at some higher frequency, if you look at the current I, which you see here in this meter, and frequency, as he increased the frequency, he didn't see anything. And then all of a sudden, at some frequency, he saw a huge current. And then if you increase the frequency further, you see that constant current coming out. His conclusion was that, hey, for the lower frequency light, such as red light or yellow light or even blue light, nothing happens. But when you have ultraviolet light, all of a sudden you'll see that electrons are emerging from this side, from the negative side, and are attracted towards the positive side, and they establish a current. Now a flow of electrons are establishing a current here. And that was a phenomenon that led him to say that when you hit the electrons on the surface of a metal, so you have a metal here, and obviously there are electrons everywhere, and if you hit it with if you hit one of these with the right frequency, so this is called a photon, and its energy was H times its frequency, that caused this electron to get out of that piece of metal and contribute to the current, so he could see the current. He concluded that this is acting like a particle. When it hits a surface of this metal, which has a lot of electrons there, you remember, you can rub electrons from surface of materials, right? There you go. You hit this with the light of a certain frequency or more, and then you get an electron coming out. So one particle hitting another particle, and that particle gets out of the surface of the metal. All right? That was his contribution to show that light also behaves like a particle. Now, in order to get this electron out, you need to have enough energy. It's called work function, which relates to binding of potential energy that holds all these electrons within that piece of metal. if you can overcome that amount of energy, this electron is going to come out with a certain velocity and has kinetic. So that energy of photon converted to this energy of this electron that is released and has certain amount of kinetic. Actually, the intensity of the light that is hitting these electrons, if you have more photons, you get release more electron. But they all have the same frequency, so they all have the same energy. The light that you use, you can increase intensity, then you get more electrons released. This was a very important phenomena and experiment. Now we have a situation because Planck said that this photon that is behaving like a wave with a certain frequency, propagating in space like a wave. And then Einstein came and said when this photon interacts with a particle or an electron, it behaves like a particle, and one-to-one it transfers its energy to that electron. And it does that immediately because the experiment tells you as soon as you hit this threshold frequency, or cutoff frequency, you may call it, current establishes right away. Okay, so it's not a gradual, very discrete situation, and then below this frequency nothing happens. Above, bang, you have a current. Now we call the light behaving like a particle, and we call that a photon. All right. There was another problem lingering along for a century, and that was about the situation with spectrum light that is emitted from different material, different elements. Well, people knew that if you shine a light, white light into a prism, and then the lights disperse, and then you get colors of rainbow and a spectrum of continuous from the white light. But they also knew that if you just heat up the one particular element, like hydrogen, and conduct experiment, you'll see only a discrete colors, and you don't see this overlap of all the colors there. And they didn't know how to explain that. They used this to identify different elements, just because you heat up an element, say neon or argon or whatever, and then you could in some of them you could see the lights. Some of the lights that are emitted is not in the visible range, but if you have a instrument you can detect those frequencies. Like sodium, you could see the spectrum and some of the yellow lights there. Therefore they use this to identify elements, but they didn't know where they come from. And then there was another complementary experiment. Now you have a white light, but put in front of this white light, put a gas, hydrogen gas. You can put any gas of any element, but let's put hydrogen gas because we saw the hydrogen gas emission. Now what you see here, because the white light is coming, you'll see all those rainbow colors smeared. However, you'll see a black or absent of the color or frequency at certain frequencies, and that's the absorption spectrum. So it happens that all these lines that you see, let's say 656, 486, 410, 434, coincide with the color one, 656, 486, 434, 410 of the emission. So this is called absorption spectrum, and this one is called emission spectrum. And that was great, but they couldn't explain why do we have this. They even came out with some relationship that explains these patterns. So they say that, let's say for hydrogen, if you want to find out the corresponding wavelength, so if you want to calculate this wavelength, where they are, they saw the pattern repeats, so they came up with empirical formula. The formula was 1 over lambda times some constant. Again, that constant was developed empirically by many experiments. So it's 1 over 2 squared minus 1 over n squared. Now 2 squared you could put 1 over 4, but there is a reason we have this, so that you'll see that later. 1 over n squared for n starting from 3, 4, 5, 6. And this r value is a constant, and it's, that constant unit is per meter. So this was actually developed by Johann Balmer back in 1885, but they had no clue that why this happens. So let's just do an example here. So suppose we want to know what the wavelength of the violet line is. So we just count the number. So it happens n is equal to 6 for the, when you look at the violet light. And then you just put that in that formula. So 1 over lambda is equal to that constant times 1 over 4 minus 1 over 6 squared, which is 36. So that gives you this number here. That's 1 over lambda. Now lambda is 1 over that, so 4.1, 10 to the minus 7 meter. And guess what? That's 411 nanometer right there. Okay, so let's watch part of this.
Now let's see how quantum mechanics helps us to understand atomic structure.
It was during the early decades of the 19th century that the structure of atoms was coming into focus. It was known, for example, that a hydrogen atom contained 1 proton and 1 electron. But the scientists of the time could think of no stable arrangement of the 2 particles. It was known that a proton and any atom were grouped in a small central region called the nucleus, and that the electrons were somehow arranged in comparatively large distances outside the nucleus. But in hydrogen, if the electron were stationary, it would fall into the nucleus, since the charges on the particles would cause them to attract one another. Yet the electron couldn't be in orbit circling the nucleus either. Circular motion requires consistent acceleration of circling body to keep it from flying away. But the electron has charge, and charged particles radiate light when they are accelerating. So an electron in a circular orbit would radiate light and would spiral into the nucleus.
Okay, you can watch the rest later on, and so let's just take a quick break and we come back. Contemporary to Einstein and Planck, there was another scientist, Niels Bohr, that he benefited from the theory that was put forward by Planck and Einstein, and then he was studying the hydrogen atom, and he came out with the idea that the electrons orbiting around the nucleus, but in a very specific manner. He described that as electron orbits to be a discrete state or orbit. Each electron basically stays in that orbit and cannot orbit in continuous manner around the nucleus. And he described that as a shell model. So the electrons are within a shell and orbiting around the nucleus of atom. His model only allowed certain orbits exist in an atom. And when electron is in that orbit and shell, they're kind of in a stable condition and they are not radiating anything. However, the electrons can receive energy via some sort of radiation, as it was shown in the photoelectric effect, and they can also emit radiation. Now, in order for them to emit radiation, they have to jump from the higher shell to a lower shell. In other words, we have the nucleus, and then we have these shells. So the electrons can go from the higher shell to the lower shell, jump to the lower shell, and by doing so, they emit some radiation. Okay, and by this process, they can even jump to, say, even lower shell and emit a different frequency radiation. Of course, if they are at some lower energy, if you hit them with some photon, they can jump up to a higher orbit. This process kind of agreed with what Planck and Einstein found out. It was very nicely put together for the hydrogen atom. And this emission and absorption of light or electromagnetic radiation was in a discrete value, because the frequencies were discrete and very specific numbers. Okay, you just multiply that by the Planck's constant, you get a discrete amount of energy. So there you go. He was able to explain why there is these discrete line of emission from the spectrum line of hydrogen, and how that relates to the jumping up or down of electron. So if the electron jumping down to a lower energy level, lower orbits, they emit those frequencies that you saw, those colors, line colors that you saw earlier. Now, if you shine a light on them, specific light, they jump up to the higher and they absorb that energy. So when the white light is shown on the cold hydrogen, the red or the blue or violet part is missing, because those are absorbed by these electrons at the lower energy level to go up to a higher energy level. Now there are more levels, of course. I'm just draw 3 for the sake of argument. Knowing the Planck's constant, knowing that Einstein's photoelectric effect, Bohr came out with a very nice relationship for the energy levels or energy of the orbits of electron around the hydrogen atom. And he basically said, if you want to find out the energy of electron in a certain orbit, let's say, shell number 5, all you have to do, you take the energy of the first orbit, divide that by that number squared. If it's 5, so it would be 5 squared. What is that first energy level? Well, experimentally they were able to find that is minus 13.6 electron volt. Now, electron volt is another unit for energy. We know the unit for energy is joules, right? So the relationship between electron volt and joule is 1 electron volt is 1.6 10 to the minus 9 joules, okay? Because it's such a tiny energy, therefore we just have to use a simpler version. So we use the electron volt. So keep that conversion handy in case you need it. So there you go. Bohr's energy level in a hydrogen atom described as energy shells 1, 2, 3, 4, 5, 6, all the way to whatever until you get to the zero. Now notice that the closer you are to the nucleus, it's harder to take that electron from the nucleus out to the space outside of that atom. Therefore, the lowest energy level for hydrogen was minus 13.6 electron volt. The second one was this over 2 squared. And the third one is minus 13.6 divided by 3 squared to be what? Minus 1.51 electron volt, and so on. So his explanation really nicely matched with all the experiments and results they obtained. Let's now watch a little bit of this. Continue.
Niels Bohr proposed the first working model of the hydrogen atom. In the Bohr model, the electron circles the nucleus as if it were a planet going around the sun. And with a nod to energy quantization that Max Planck dreamed up for solving the ultraviolet catastrophe, Bohr said that inside the hydrogen atom, the electron was allowed to have only discrete values of angular momentum in its orbit around the nucleus. Translated, this means the electron can occupy orbits only at certain distances from the nucleus. And Bohr simply dismissed the problem of an electron radiating away its energy by stating that it just didn't happen. Even great scientists cheat sometimes. He postulated that inside an atom, electrons only radiate energy when they jump from one allowable orbit to another. And the energy of this radiation reveals the allowable orbits. The wavelengths of light absorbed by hydrogen when white light is shined upon it, as well as the wavelengths of light when it is subsequently re-radiated, had been precisely studied at the time but never explained. Here's a sample of an absorption spectrum and an emission spectrum. By predicting the value of orbits that an electron could have, Bohr's model also predicted the wavelengths of the lines in the hydrogen spectrum. And his model was tremendously successful. It explained in exquisite detail the atomic spectra of hydrogen. When the energy of the wavelengths of the spectral lines are compared to the energy differences in orbits allowed in Bohr's atom, they agree exactly. So the quantum approach worked well in explaining the allowable orbits. But no one was certain why only those orbits were allowed.
So now, Bohr has a very interesting theory, and it works well with the hydrogen atom, and all the spectrum line frequencies and wavelength provides the proof of this model. What was the problem with Bohr's model is that it works well with one electron and one proton for hydrogen atom, but it didn't work for helium or other elements which had more than one electron. And that was another challenge for scientists to overcome. Now this is, early 1900s, and everybody was very active, and people coming out with new experiments try to resolve this. And the question was that now we know that light behaves like both particle as well as waves. Then what prevents us from thinking about particles like electron, proton, neutron, and even atoms? Why can't they behave like a wave? Now that was an interesting question. That was answered by de Broglie. 1923, he actually proposed that if you have a particle that is moving, an electron, and that electron has a velocity of v. Once it has a velocity, obviously it has a momentum, because we know electron has a mass, so momentum is equal to mass of electron times its velocity. But as long as this electron carries enough momentum and is moving in certain velocity, it has to move around certain velocity, it behaves like a wave. The electron that we knew that was a particle, which has a negative charge, now when it's moving, it can behave like a wave. And that was a revolutionary idea, as long as it moves with certain velocity. It has a wavelength. What is its wavelength? Well, he said this wavelength is equal to, again, he used this constant, is coming to play again, Planck's constant, divided by its momentum. Its momentum is mass of electron times velocity. So that is the game changer, because now we can think of all the particles in atomic scale to behave both like a particle as well as like a wave, just like photon. So this tells us a dual nature of matter. Experiments could prove that, and they did. They used a certain matter, and they shined the X-ray through it. X-ray is electromagnetic radiation, is wave, we know that. and they saw this interference pattern or diffraction pattern on the screen. So if you send the X-ray through the hole, you see this diffraction pattern. That hole must be at the order of the wavelength of the X-ray. Then they tried electrons sending through the little tiny hole, and lo and behold, they saw a diffraction pattern, because now electron is behaving like a wave. A revolutionary, right? And it helped to further develop the quantum theory. We know this. These electrons that are going around a nucleus, they're behaving like a wave. It's not like just a nice circle orbit. It's behaving like a wave going around them. Now let's just recall what we learned in the wave chapter when we talked about waves. Remember when you had a string, you tied to the doorknob and you would go up and down on it in the right frequency? What do you get? You get a standing wave. And then if you change the frequency in the right amount, then you get the second standing wave and the third one, but nothing in between. We did an experiment. I showed you the demo of a ring that set to oscillate, and then at certain frequencies you were able to see these standing waves, not in between. Very important. Now we are bringing this to an atomic model, the Bohr's orbit. And we say that the orbit of these electrons that are now behaving like a wave can actually form a standing wave and stable condition for discrete orbitals, provided the circumference of that orbit is multiple integer of the wavelength of the electron that is oscillating, behaving like a wave. If that happens, you get a standing wave. But if circumference is not multiple integer of the wavelength, so circumference of the orbit is 2 pi r, is not equal to multiple integer of the wavelength, then you will not get a standing wave. And that agreed with the Bohr's model that you have shells and you have forbidden region that electron cannot exist in between those shells. It can only exist in those discrete shells. Now these shells are actually like a wave spread throughout that circumference or sphere in 3 dimension that we will see. It will be a cloud of electrons. Now we can relate the wave aspect of the electron to its orbital of different energy level around the nucleus. You can have n equal to 1, so that would be one wavelength forming over the entire orbit, n equal to 2, n equal to 3, 4, 5, 6, and so on. That actually agreed beautifully with these de Broglie's wave and particle duality nature of electron, or in general atomic particles. So now you see the concept of a standing wave that we discussed before now helping us to understand stable orbit of electron around the nucleus. Because the electrons are stable in those orbit, they're not going to emit any radiation because they're just oscillating in the form of a standing wave. They're not going to dissipate energy, okay? The only time they give off energy if they jump from the higher orbit to a lower orbit. So if we have an electron that is behaving like a wave, so why not we explain this mathematically in a form of a wave function, a traveling wave function. And that was a beginning of the concept of quantum physics. So this wave function in the form of a standing wave, it's as a result of many waves superimposed and provide you with this nice wave function. Okay, so remember when we talked about the waves, you could have the, let's say, the first fundamental, or you could have the second, or you could have the third and fourth and so on. And if you add all of these, you end up getting a wave function that could look like this. Any wave function can be actually decomposed with the simpler harmonics of a sinusoidal wave. And this was actually proven by Fourier, and vice versa. If you add many harmonics of sinusoidal waves, you can produce any kind of wave function that you desire. So let's just continue the remaining of this video.
In his doctoral dissertation in 1924, Louis de Broglie put forward a simple idea that significantly advanced the understanding of the extremely tiny. A quantum leap forward, you might say. Since Einstein and Planck and Compton had firmly established that light could have the characteristics of both a wave and a particle, de Broglie suggested that matter particles, protons, electrons, atoms, billiard balls, could sometimes act like waves. And when this idea was applied to Bohr's atom, it answered many questions. First, the allowed orbits had to be exact multiples of the wavelengths calculated for the electrons. Other orbits produced destructive interference of the waves, and soon the electrons couldn't exist there. So the circumference of the orbit must equal the wavelength, or twice the wavelength, or 3 times the wavelength, or for that matter, any multiple of the wavelength. Second, these orbits weren't really orbits in the traditional sense. These electrons didn't travel around the nucleus in a circle. Rather, they took the form of a standing wave that surrounded the nucleus entirely. The exact position and momentum of the electron particle could not be specified at any given instant.
De Broglie's particle waves seemed to answer many questions, but this was still not the final answer.
All right, well, we are getting there. Another things that people were struggling with is that how do we measure some of these quantities that we do in classical mechanics, speed of a ball, speed of a bullet, or position of a ball that you kind of throw in a trajectory or in a circular motion and so on. We know that we can measure those quantities pretty exact in classical domain, but when you go down to the atomic scale, can we measure these things precisely or with certainty? No. And all the measurements that are made in atomic scale is in the form of a probability. What is the probability of an electron to have range of positions? So from this point to that point, let's call that a delta x. What is the probability? Well, you can say, okay, probability can be high in the middle and low at the corner, so you can show the probability with some sort of a curve. Say, okay, the probability is high in the middle and it gets lower and lower as you go to the two ends. Then Erwin Schrödinger in 1926, now look, from 1900, beginning of 1900 to 1926, a lot of things are happening. And he actually came up and mathematically showed these wave function. He called that a psi as a function of r, which is position. R could be, in x or y or z position. Psi is the wave function. And wave function basically can have a very complex form like this. And it basically tells you information about how the particle or electron is behaving in that region. So if we have a region here, from here to there, it's a delta x. That's how it behaves in that region, and is a traveling wave. Remember, the waves go back and forth, between 2 points and produce standing wave. And the equation that governs this, which you don't have to worry about it, is just I'm showing you here, just to get a overall kind of concept from it. It's an equation of conservation of energy. It says the kinetic energy of the particle or electron plus its potential energy has to be equal to the total energy. Okay? Kinetic energy times its wave function plus potential energy times its wave function plus is equal to total energy times its wave function. This is called Schrödinger's. And I have a very nice video animation that shows this. Don't worry about the details of this, but one thing you want to notice that these wiggly waves are the wave function between, for example, 2 points. The wave function could be constrained between 2 points or a volume in atom, okay, in a box, 3-dimension or 2-dimension. In this case, the wiggly thing is wave function. Now, if you square this wave function, you get psi square, which is related to probability of the position of that electron. So this black one, it gives you the probability. The particle is more probable to be right there in the center than here or there. And of course, depending on where this particle is, electron is, if it is in a box, you have a constraint on ends of the box. Just enjoy this video. So here's the potential, and here's the particle that is oscillating within that potential. Well, so that's the wave function, red, and the blue is the probability of that particle, or say electron, that is going back and forth between these two walls, or in this form. Imagine a skater just going up and down here. Okay? Now here's one that is traveling and there is no potential. It just wave function is traveling and dissipating, and the probability is reducing. Now here's the barrier here, and the wave function of the electron is coming and entering and reflecting back. Here's the step. Here's the well. Now notice the wave function that was coming and falling into the well, part of it basically goes to the other side, and part of it reflects. What does that tell you? The blue line tells you the probability of that electron to jump over is higher than stay in this well, or fall into the well, and the probability of electron to kind of reflect back is a little bit higher, but lower than this side. Just the obstacle entering. Now, here you have a wall, and the electron comes in, and part of it, probability of some that reflects is this much, but there is a probability that this electron tunnels through that wall to the other side. There is a small probability that this is the concept of tunneling. So in atomic scale, you can actually, particles can tunnel through a barrier. Okay? But if we try to, go through a wall, obviously we, we fall down. We cannot, go through it. But the electrons, if they see a barrier, there is a probability that they can go through. It's two barrier. Now, okay, saw that. Now you see some probability that is more probability that is going to reflect, some probability that's going to go inside this barrier, and some probability that it's going to pass through both. Okay, so you can watch this on your own again if you like. Just give you some idea. Okay, we are at almost mid 1900s, and now we have a theory, is a quantum theory that describes the atom. Now this from the evolution of just a simple Bohr orbital model to de Broglie wave model of electron orbiting the nucleus. Now we get to this Schrodinger's equation that provides a probability. The orbits are like a cloud of probabilities that electrons can exist in those orbits. It's more probable to be on those orbits than anywhere else. And those are explained with the Schrodinger's wave function and its probability. Question for you as why electron orbit in only certain orbits? A compelling explanation views orbital electron as, very important, as standing wave. Let's do an example here. Suppose we want to find out the what is the wavelength associated with the electron that has a velocity of 10 to the 6 meter per second. Electrons are moving that fast there, velocity of light is 10 to the 8 meter per second. So we're getting close to that velocity. And the mass of electron, we know what it is now. Okay, so all we have to do use de Broglie relation. Lambda is equal to h, Planck's constant, divided by mass of electron times velocity. So just plugging all of that, what do you get? You get 1.2 10 to the minus 10 meter. So the wavelength of the electron is comparable to the size of that atom. Remember, we talked about atomic size and the order of angstrom. So there you go. One more thing to resolve, and that was the issue with the discrete line values. And Balmer series that we saw, which is in the visible portion of the electromagnetic radiation, which we can see those lines that you saw in the spectrum, remember 410, 434 nanometer, 486 nanometer and 656 nanometer, those come from electrons jumping from, for the 410, jumping from the 6th orbital to the 2nd. And the rest is, from the 5th to the 2nd, 4th to the 2nd, and 3rd to the 2nd. These series is the one that we can actually see with naked eyes. But there are other jumps, say from 6 to the 1st. We don't see that, but you have instrument to detect that. Or from the higher orbit to the 3rd. That's called Paschen series. This up here called Lyman series. So these were verified with the new theory, new quantum theory, and the discrete spectrum line were explained and resolved. If you look at the hydrogen atom, rather than drawing those circles, let's just draw a line representing those orbits. N is one ground state, we call it, and then N2, N3, and these are the ones that correspond to those lines that we can see in Balmer series. The transition from higher state to the second state. And the Lyman series in the ultraviolet region, which we don't see, and the Paschen series in the infrared region, which we don't see, but we can detect with our instruments. The lowest energy level is called ground state, and these other ones called excited state. The thing that we need to pay attention that the energy of these photon that is emitted, let's say from 6 to 2, which is 7 is equal to h times that frequency. Okay, that's frequency is 7.3 10 to the 14 hertz, and it's a discrete value because this frequency is fixed. H is a fixed number, so that gives you the discrete amount of energy. Okay, the wave function was developed by Erwin Schrödinger, and the Schrödinger's equation, very famous equation, as you saw, works for not only hydrogen atom but all the other elements. And then it actually relates to all the things we use in chemistry to look at the properties of elements and how they react with each other as a result of all these quantum theories and findings. Energy of electron can be described with 4 numbers. The first number represents the main energy level orbital, called the principal quantum number. Start from 1, 2, 3, 4 all the way to infinity, which is when the electron can exit from that atom. The second is energy of sub-level. Now it turns out that each level, say N1, N2, N3, and so on, each level can actually have a sub-level. And those sub-levels happen because of the angular momentum of these orbiting electrons. And those are shown by letter L as SPDF. So this is called angular momentum quantum number. Now, if you have a magnetic field present, then these orbitals can also further divide in sub-levels, orient themselves in a different part of the space, and that's called magnetic quantum number. When you look at S, you have one orbital orientation. So everything is kind of a uniform, is like a sphere. When you talk about P, then you could have 3 different orientation, an X and Y and Z axis. And then D and F and so on, you would have more possible orientation. That's called quantum magnetic number. Then electron themselves can have also 2 configuration. One is that while they're going around the orbit, they can also spin around themselves with a positive spin up or negative spin down. That's a spin quantum number. So 4 numbers can explain the condition of a given electron, what state it is, what is this energy. And those are shown, as you may have seen, in these forms of a cloud. It's not like a definite orbit, it's a cloud of probabilities. Now we have S is a cloud of probability of a sphere, that there is more probability of electron to be on the surface of this sphere than close to the nucleus. So if you kind of look at this probability, it looks like something like this. The nucleus is here, and this is the distance from nucleus. So the probability of electron on an S orbit is like, being in the distance of first orbit R1 from the nucleus. P orbital, you have probability of having orientation in space in X and Y and Z, gives you a probability. You see, the probability vanishes near the nucleus. There is a very small probability that electron exists in the nucleus. There are more probabilities that are way up in these radiuses or these orbitals. And then if you combine these, you get, this is a D orbital and so on. And of course, you have the spin of electron itself, so it provides you two configurations. If you see these electron orbitals in the form of a cloud, that's what it means. And this is combined, say, S and P state together. And you can combine a lot more, but it gets a lot more complicated. Not easy to recognize those. Now, we can see that elements, their position in periodical table relates to their electronic orbitals, and it can very nicely be arranged in the periodic table based on their number of shells, number of orbitals, and number of electrons in each one of those orbitals. Okay? And we'll talk about this in a minute. Now, arranging these elements in the periodic table, you need to keep in mind that same electron with same set of quantum number cannot coexist one orbital. Exclusion principle, which was put forward by Pauli, that electron has a unique set of quantum number. So each electron has its own unique quantum number. There could be two electrons in s orbital, but the quantum number differs by spin up or spin down. That is very important. That's why you can have certain amount of electrons in certain amount of orbitals. When you look at the electron configuration and these quantum numbers that we talked about, these are principal quantum numbers, and 1, 2, 3, 4, 5, and so on. So the first one is energy level is S, and you can take only 2 electrons in there. The second level energy has S and P. Now S can take 2 electrons, but P can take up to 6 electrons because there's subshells. Total of 8 electrons. For N3, S can take 2, P can take 6, and D can take 10. For N4, S2, P6, D10, F14. So total 32. And you can go on. How do we write this electron configuration? Well, we start with how many electrons we have, and then we just fill the shells. It's just like, think about an apartment building from ground state. Ground level of the huge apartment building has only 2 apartments. So you fill that with 2 tenants of different quantum number. The second one has 6 apartments. So you can fill that with 6 tenants, and so on. So if you take 36 tenants, so it takes electrons, let's see how many levels we have to fill in. Well, the first one, 2, the second one, 2 in a S, 6 in a P subshell, and the third is 2 in S, 6 in P. Now, sometimes these sublevels of the lower orbital has higher energy than the next orbital. In this case, the 3 has S2 electron, P6 electron, and then 3D, which has 10 electron, it's higher than 4s2. 4s2 has 2, and then 4p has 6, and the remaining, if you just count all the electrons here, 2 plus 2 plus 6 plus 2 plus 6 plus 2 plus 10 plus 6, you're left with 2, which it would be a 5s2. So that would be a strontium electron configuration. Now you may say, how do I arrange this? Well, it's a simple. There's a chart here that tells you how to do this. So you start from 1s, you go to 2s, you go to 2p, and 3s, and then 3p, and then 4s, and then 3d is right here now, okay? And just follow this order, and you get your electron configuration. The last electron is the very important electron called valence electron. And that's what, in chemistry, it basically responsible for all the reactions between elements. Here's another representation. So the first n is equal to 1, it got 1 level, period. N2 you have S and P. Okay, so there's a subshell, sub apartments in the high rise. The third one has 3S, 3P, 3D, but 3D is higher energy than 4S, which is the next main orbital. Okay, 4P, 4D, 4S. And here's more with the number of electrons. You see that the first one only has 2 electrons. One is spin up, one is spin down. Okay, and the second one, again, one is spin up, one is spin down, and then P is 6 of them. And these spin up and spin down, remember, at the valence electron would contribute towards the magnetic property of that particular element. We talked about that. How does electron orbital relate to periodic table? Well, what do we have in periodic table? We have 7 horizontal rows. Now these rows, periods, shows the configuration of number of shells for the elements. And then you have 18 vertical columns. If you look at the kind of raw structure of the periodic table, these are the groups and these are the periods, horizontal periods, 7. And of course you have these transitional elements and so on. So we're going to concentrate only on the groups of A, 1A, 2A, 3A, 4A, 5, 6, 7, 8. So we're not going to talk about these transitional elements at this point, or these inner transitional elements. Okay, it's beyond the scope of this course, but let's just look at those elements there. And let me bring a full periodic table here. So what do we have here? These 8A group, they are the noble gases. And as you'll see soon, all their apartments are occupied by tenants. So they don't want to accept any more tenants or give away any tenant. All their shells are occupied with electrons. They don't interact, they're inert. Group 1A, 2A, 3A. So 1A, 2A, and 3A. Okay, these are metals. They usually lose their outer electron, and once they lose outer electron, they become ion, positively charged, and they will attract anything that is negatively charged. Group 5A, 6, and 7, these are nonmetals that like to gain electrons. So if these guys are giving an electron away and these guys are gaining, guess what? They really like each other. These become negatively ion, these become positively ion, so there's a lot of interaction between these elements and those elements there. So a lot of compounds, a lot of new substances are generated or produced by reaction of these and those. And then group 4 right here is mostly semiconductor, and we talked about semiconductor earlier. Now the metallic characteristics of element increase as you go down, you go from top to bottom, have more metallic characteristics. And they decrease across a period. So if you go from left to right, they become less and less metallic characteristics, as here we have, some gases. Valence electrons are the important electrons, and they're responsible for chemical reaction, chemical bonding. For any group, they all have the same number of valence electrons. So once they have the same number of valence electrons, they chemically have similar properties. So take a look at this. Is a very important part of the periodic table, which connects to the orbital shells that we talked about. So if you look at group 1A, 2, 3, 4A, all the way to 8. So we're ignoring all these things here. So 1A, 2, 3, 4, 5, 6, 7, 8. Look at the shells. On this period, horizontal, they have one shell. Period 1, they have one shell. On the second row, they have 2 shells. On the third, they have 3 shells, 3 main principal numbers, and so on. So periods represents number of shells. Now, columns represents number of valence electron. Hydrogen has one valence electron. Lithium has one valence electron. Sodium has one valence electron. Fluorine has 7 valence electron. Chlorine has 7. You see that? All the noble gases, the valence electrons are full. So no vacancies here. Here there's one vacancy. So here there are 2 vacancies. Okay? 3 vacancies, 4 vacancies, and so on. So number of valence electron is group number. Number of shells is period number. Very important. As far as the size of these atomic elements, well, as you increase the shells, as you go down the groups, number of shells increase. So you expect that the atoms get bigger and bigger, size-wise, right? Which is fine. Yeah, it does. You see, you're coming down, it gets bigger and bigger. More shells, you get bigger atom. Now, you go across, period, although there's more electron involved as you go across, remember, you go across here, you have 4 electron here, you have 6, you have 7, all right, 9, okay? But what's happening? The size of the atom gets smaller, and that's because more negative electron and more positive proton, they have more of an attractive Coulomb force between them, so they're tightly squeezed together, and the size of the atom becomes smaller as you go this way. So you see how nice orderly this periodic table reveals a lot of things that quantum physics explains. The last question is that how precisely we can measure physical properties of these atomic particles. Well, it turns out that we cannot. We only can know a probability. They can measure things in the form of a probability. What is the probability of that electron to be in that orbital? Maybe 80%. Because we have this wave nature of matters, and electron position, velocity, can not be able to measure them precisely. In fact, if you measure one with more certainty, you lose the measurement of the other one. For example, if you measure the position of an electron with delta x probability, then you lose certainty of measuring the velocity of that electron. And if you want to measure the velocity of that electron with more certainty, as a result, you lose the measurements of its position. So this is how these parameters now relate to each other. Knowing more about, knowledge about position of a particle, you lose knowledge or information about the velocity of that particle, and vice versa. And that was put forward by Werner Heisenberg in the form of Heisenberg uncertainty principle. So in other words, the uncertainty of a position, time uncertainty of the velocity or momentum, it's equal or greater than a fixed number. That fixed number is h, which we know what it is, and pi, we know what it is, h over 2 pi. And one good application of the wave nature of the electron is we can use that to measure an order of the atomic size particles. Remember, when you look at a macroscopic particle under the microscope, what do? You shine a light that's visible to us. The wavelength of that light is around 400 to 700 nanometers. So we can resolve things, particles or microbes or pollens that are order of that size. Because if we have a smaller, that wavelength is so large, it just passes by, it doesn't reflect back. Because what we see is as a result of reflection from those particles. And Therefore, we cannot resolve things smaller than those wavelengths. Now, we have an electron that has a wavelength of around 1 nanometer or less. We just calculated that, remember? So we can use that to resolve atomic sizes. We shine that electron, send that electron wave to interact with those atomic size particles, and it reflects back, and that reflection is registered as an image of that particular object that we're trying to resolve or see. And this is a picture of an electron microscope, pretty elaborate. Bombard or send electron beam onto a species that you're trying to resolve, and then you are able to see that. Here's some example. Here is you may be familiar with this image of the coronavirus. Here's the head of an ant. Here is the picture of the silicon crystal formed on the surface of a silicon. Here's the picture of hydrogen atom, all taken with electron microscope. All right. This is a very good, it's 1 hour video that I'd like you guys to watch. And it's a very interesting, good video to watch. And we may come back and talk about some of the things that are discussed in this video. So please go ahead and make sure you watch this video, so that when we talk about some of the factors, you're familiar with what I'm talking about. Okay? This concludes the chapter about atoms, and I will see you next time.